Myself, T. Paramesh, Assistant Professor in the Department of Aeronautical Engineering, SJS Institute of Technology, Chikbadapur. Today we will discuss a very important concept, flow through the various passages in aerodynamics 2. We will see the contents of this concept. Here we will discuss briefly on subsonic flow through the nozzle, subsonic flow through the diffuser, and then supersonic flow through the nozzle and diffuser, and flow through the convergent divergent nozzle. Okay, so before going to the nozzle diffuser, so first we will clearly understand the area pressure relationship and the area velocity relationship. So you can see here we have, so dA by A, this is the area pressure relationship, and this is a velocity area relationship. So you can see here, if the flow is subsonic, so that is, I am considering the flow to be subsonic. So if the flow is subsonic, 1 minus ma square component will be a positive quantity, and then whatever the sign that we have for the dA by A will be the same for the dB by rho v square. That means that if the area is decreasing, pressure also decreases. The same thing, if area is increasing, pressure increases. Next, so the same thing, we have the area and velocity relationship. So since the flow is subsonic, ma is less than 1, so that is, this component will be a positive quantity, and then dA by A is a negative of dV by V. That means that as the area increases, see, when the flow is subsonic, as the area decreases, velocity increases, and the reverse, when the area is increasing, velocity decreases. Fine. So we will discuss for the supersonic flow. If the flow is supersonic, that means that ma greater than 1. So what happens? So this component, 1 minus ma square component, will be a negative component, and then finally I can write it as dA by A is a negative of dB by rho v square, and then here we can see here, so dA by A is a positive component of dV by V. Thus, when the flow is supersonic, please observe here, so supersonic flow, when the flow is supersonic, as the area increases, pressure decreases. It's a reverse. And then as the area decreases, pressure increases. Fine. And then it is the same with but we have the same relation. As the area increases, velocity also increases. As the area decreases, velocity also decreases in case of supersonic flow. Also, we will see, since the velocity is increasing, so Mach number also increases. So since the velocity is decreasing here, Mach number is also decreases. So similarly here we have, since the velocity is increasing, Mach number also increases, and the velocity decreases, Mach number also decreases. So here we have, next we will move to the slides where here this is the analysis of a subsonic flow through the nozzle. So why we are calling this shape as a nozzle? Because in whatever the duct we take, if the flow is accelerating through the duct, then we call that as a nozzle. So here we can observe here, so this is a static pressure, so the variation of static pressure through the nozzle, and this is a variation of the dynamic pressure through the nozzle, and this is a variation of total pressure through the nozzle. Observe here, so as it passes through the nozzle, static pressure is decreasing. I think you can see here, so this red color represents the highest component, whereas the blue color represents the lowest component. So that means that the static pressure is decreasing through the length of the nozzle. Whereas what happens to the dynamic pressure? So dynamic pressure is half rho v infinity square. So that is v, the velocity is increasing. Hence here we can clearly observe that since the velocity is increasing, so through the dynamic pressure is increasing through the nozzle. Whereas what happens to the total pressure? So total pressure remains constant. Total pressure remains constant through the flow of the nozzle, through the nozzle. Next, so velocity, what is happening to the velocity? So if you see, as it passes through the nozzle, velocity is increasing. That is why we are calling, if the flow is subsonic, we are calling this passage as the nozzle. So So what is happening to the static temperature? Here we have static temperature. Static temperature is also decreasing. So next we'll go through the subsonic flow through the diffuser. So here I have kept three things. One is the static pressure, the other one is the velocity, and the other one is the temperature. So clearly we can observe that why we are calling this passage as a diffuser. So the main reason is as it passes through the length of the nozzle, the pressure is increasing. Hence we are calling this as a diffuser. Observe here static pressure. So since this red color represents the highest component, so as it moves through the diffuser, the pressure is increasing. So next is the velocity. We can see here the velocity is decreasing as it passes through the nozzle, and then here you can observe that the static temperature is rising through the diffuser. So next we will discuss on supersonic flow. Now observe the supersonic flow through the nozzle. So why we are calling this as a nozzle even though it is divergent? So the main reason is, so we are not calling the nozzle or the diffuser based upon their structure. So the main thing is it should supposed to serve our purpose, that it should accelerate the flow. So observe here what is happening to the static pressure, velocity, and the temperature. So you can clearly observe that even though it is divergent, if our inlet velocity is greater than Mach 1, then clearly you can observe here is shock formation is being formed, and then the static pressure is decreased through the nozzle, decreased along the nozzle. Next, velocity is increased through the nozzle, and then here static temperature has also been decreased through the flow through the nozzle. So the opposite happens with the diffuser. Observe here. So we will discuss supersonic flow through the nozzle. Here, even though it is convergent in structure, since if the inlet velocity is greater than 1, we can clearly observe the static pressure is decreasing through the nozzle, and static pressure is increasing through the diffuser, velocity is decreasing through the diffuser, and then static temperature is increasing through the nozzle. So that means that if you see, we should supposed to have a different structure. So if depending upon the flow velocity, consider here if the velocity is subsonic, that is Mach number is less than 1, so this portion, this represents the nozzle, and if the velocity is that is if the Mach number is less than 1, this will be the diffuser. If the velocity is greater than 1, this shape will be the nozzle, and if the velocity is greater than 1, this will be the diffuser. So here we can clearly observe that if the inlet velocity is subsonic, we cannot accelerate much to the exit, and then here also the same, if the Mach number is greater than 1 at the inlet, we can obtain the supersonic speeds. But how to obtain a supersonic speeds at the exit even though if our inlet velocity is less than 1? So that is inlet Mach number is less than 1. So for this we will move to the next portion, convergent divergent nozzle. Yes, you can see here convergent divergent nozzle. So why this convergent divergent nozzle is required? So if you see the subsonic nozzle or the subsonic nozzle, if the inlet velocity is, that is if the inlet Mach number is less than 1, so the maximum Mach number that can be attained at the exit of the exit of the subsonic part is only Mach 1. So it will at the inlet we will have less than 1, but at the exit of the subsonic Mach number nozzle, the maximum Mach number that can be obtained is 1. Since in order to increase the velocity of the flow from a subsonic speeds to a supersonic speeds, we need a convergent divergent nozzle. So even though if our inlet velocity is less than 1, that is Mach 1, our exit velocity, supersonic velocity will be greater than 1. So for this purpose we are using convergent divergent nozzle. So you can clearly observe thus what is happening to the static pressure. So as it passes through the convergent divergent nozzle, static pressure is decreasing and a shock is being formed, and then still the static pressure decreases through the nozzle. Whereas here, so the velocity is increasing from subsonic Mach number to a supersonic Mach number. Here static temperature is also decreasing as it passes through the convergent divergent nozzle. So we can understand so why in the divergent section the Mach number is increasing. It is because of due to large decrease in the density. Hope you understand. For more videos, visit my website